G'day folks, and welcome back for another Chem 1011, Chem 1051 video tutorial. So in the last tutorial we were talking about converting wavelength to frequency or frequency to wavelength using the wave equation. But in this video I want to talk about interconverting between energy and frequency. So this is the same frequency we talked about in the previous video when we talked about the fact briefly that understanding light and the nature of light was really important for understanding atoms and molecules. Now, there is something a little bit weird about light. It has sort of weird behaviour. It's often what's called wave-particle duality, and we'll talk about that in more detail in the lectures. But the wave nature of light alone doesn't correctly explain a whole bunch of things that we see when light and matter interact with one another. So, for example, the classical sort of model doesn't really correctly explain the distribution of wavelengths emitted by a glowing object. Now, that's a very detailed conversation, which I'm not going to go into right now, but a little over 100 years ago, Max Planck came along and he thought he could explain this phenomenon by assuming that energy comes in packets. So, cut a long story short, we now call these little packets of energy photons. So, for example, when you're looking into the sun, there's a whole bunch of photons, little packets of energy, which are entering your eyeball. And they're from across the electromagnetic spectrum. Obviously, there's visible light, but there's infrared and there's UV and all these sorts of things. It was Einstein who came along and took Planck's idea that light was little packets of energy to explain something called the photoelectric effect. Now, once again, I'm going to give you the short version of this, but it's really interesting, so I encourage you to go away and read about it, and we'll talk about it in lectures as well. The observation was really that if you took light and you shone the light up against a piece of metal, depending on the frequency or the wavelength, which we know are interchangeable, you may or may not get electrons emitted from that metal surface. So this was kind of weird. So they were sort of thinking, even if your frequency was low, as long as you shone lots and lots of light against the metal, eventually you'd be dumping enough energy into that metal and an electron would jump off. It didn't work that way. The frequency of the light or the wavelength of the light had to be beyond a certain threshold before you would see the emission of electron. Anyway, so cut a long story short, this was taken as, if you like, experimental evidence that light was little packets of energy, not just, if you like, a continuous stream of energy which wasn't measurable in a particle sort of way. Anyway, so I encourage you to go and read about that. It's quite interesting. From a chemist's perspective, this means that these little packets of light must be little packets of energy, and if that's related back to light, which we know has wavelength and frequency properties, there must be some sort of relationship between energy and frequency. And that gives us this equation, E equals h, where h is a constant, it's known as Planck's constant, multiplied by the frequency. And so you can see here that Planck's constant is an incredibly small number, 6.63 times 10 to the minus 34 joules seconds. Not joules per second, but joules seconds. So, in summary, what might we use this equation for? Well, chemistry, we're going to see, is all about energy. Now, if chemistry is also related to light, what's the relationship between light and energy, and the energy that we use to do chemistry? So the sort of question we might get in chemistry looks a bit like this. Determine the energy of a mole of photons with a frequency of 1.66 times 10 to the power of 17 hertz. So we can use this equation to determine the energy for one photon. And this question is asking us to determine the energy for a mole of photons. Okay, now, just a reminder, a mole, it's a really big number, 6.022 times 10 to the power of 23. So let's just work out the energy for one photon. So E equals Planck's constant times the frequency. In other words, there's Planck's constant. It's the kind of thing that's given to you in an exam. You don't have to memorize that number, but you kind of get used to it after a while. Multiplied by the frequency. So it's just the frequency that was given to us in the question. Plug it into the calculator and you'll get an answer. Now the units are joules Energy is always measured in joules. And you can see it's 1.10 times 10 to the power of minus 16 joules. Now, that seems like a pretty small number, 10 to the minus 16. But that's one photon. That's an extremely small amount of light. In chemistry, more often, you're dealing with moles of atoms, moles of molecules, and indeed moles of photons. So, the energy for a mole of photons would quite simply be the answer you got to the first part, 1.10 times 10 to the power of 16, multiplied by Avogadro's number, the number of anything in 1 mole. Plug it into your calculator and you should get a number that looks something like that. So there you have it, 6.63 times 10 to the power of 7 joules per mole. You'll come across questions like this in the course, so just get used to the equation it's asking you to use and what it means when it says energy of a mole of photons. Don't get tripped up and forget to accommodate for the mole part of the question. See you in the next video.